Yeah, Yan
50 solve still.
yeah, Yan85 was level 14 and up, I believe.
Yeah.
Okay,
Into 18.
so I'm gonna go into what was this? Yeah, 14 teaching. Let me see. Do I have 14 teaching on? I have level 4 teaching. Let me re-download this. Let's go to 14. And actually, I mean, we can do one of the, or we can do at least this challenge if you want to. The problem is like the 14 one, you actually have to walk through like what his assembly does, which this is why that's why I'm like, that one's going to take a lot longer to go over. I'm going to use Binary Ninja for a little bit. And if you would like, I can also use Ghidra, but...
Wait, are you paying for Binary Ninja?
I already bought Binary Ninja. I've had it.
Oh, a subscription.
If you want updates, yes.
Oh, okay.
Yeah. If it, like, mine's out of date for what the quote-unquote newest version is. But the Binary Ninja application I have here should be similar to the one that you have on the web.
Yeah.
The only difference is you can't patch stuff. I can. But we're not going to do that here. So a Yan program is kind of broken up. So let's back up here, vim yan.notes. So every program has every assembly language, well, not every, but we'll say generally, like for like x86, for example, you have a combination of things which make up how a computer executes.
Oh wait, are you recording this?
Yeah, I am.
Okay.
Like how a program executes. So you have some idea of memory, you have your registers, you have the instructions that are going to be processed, and then you have your syscalls, which based from your OS class, like syscalls will do different things based on what the type of syscall is, but it's a way for your program to basically talk with the kernel and to do some sort of operation. So whether that's taking input from the user or trying to write to the screen or write somewhere else, you need a syscall. Most instruction sets, so whether that's x86, MIPS, all those, have syscalls, even if you may have not used it before. And Yan85 is no different. So this is what we really need to be looking for whenever we're reversing these challenges, is what section, what's going to be our memory, where is that going to be, what is going to be represented of our registers, what's representative of our instructions, and what's representative of our syscalls. You can see these inside here, actually. Let's just go to the main file. And I'm going to put this in the graph mode and put it on high level overview, or high level intermediate language. This is, oh Jesus, this is level 4. Oh, I downloaded the wrong one. Bless. Oh no, this is the right one. This is level 14. Did I get the number of the challenge wrong for the Baby Yan stuff?
No, so it'll be Baby Rev 14, right?
Oh, I grabbed the wrong 14 is why. I need Baby 14. Rev, not Baby Mem. This is why. Okay. So we will, I don't know why I closed out of Binary Ninja completely. I should have just only closed out of the one. So go ahead.
Computer architecture.
So let's see where we at. Main. So we'll go ahead and change that into this mode, and I'm gonna slap that I button. We can see here that it takes in some VM code, which is at some point in the program, and it copies it into this space. And then it passes that space into an interpreter loop. Right away, we can basically assume that this is some sort of, this is its execution. This is the memory space that the program is going to use. And the more that we start reversing this and start looking through this, we see that this variable that's being passed in this arg1 is constantly being thrown everywhere. We go to the interpret instruction. Well, arg1 is in every single one of these instructions. So everything that we use is based on arg1. And that's because that's where our memory exists. That's where our instructions exist. That's where our registers exist. The way that the memory area is broken down is you have some space that's just like your instructions. Then, so that's got, a bunch of junk within it. And then you have some space that's your just memory of some amount. This might be your, your stack, or it might have sections that are like you stored. So like if you're storing variables, or you're trying to store, I don't know, like if you want to store the word like flag, you would put that somewhere in memory, either using the stack, some sort of stack instruction, or some sort of, I'm going to write a memory here. And this would be like memset, in C. Actually, kind of like what we did here with this guy right here, this mem copy. That'd be a similar idea. So this space that's going to be right here would be all the memory that you'd be writing. This is going to have values of some sorts that you might be using later on. And then you have registers. And that's actually not a bunch of random values. These are going to be the registers that the program's using to operate. Each of these registers, there's, and also the idea of, rolling back a little bit, an idea of like an x86 you'll see are registers that have meaning, and then registers that are general purpose. And when you look at, say, like, if I GDB, I don't know, grab just one of these challenges, and I'm going to, if it loads, break main, I'm going to run, we see these registers up here. There's RAX, RBX, RCX, DX, SP, and all so on. This section of registers, whenever we look at like syscall documents, or we look at basically I think syscall is a good example of this. Whenever you look at syscall documents, you normally see them refer to at least like RSI, RDI, sometimes RCX for like how to execute certain syscalls. So those have to be specific values in those spots. Now these, you hardly ever see anything refer to R8 through R15. That's because those are called general purpose registers. When they are referenced, it's because we didn't have enough regular, like, useful registers to store that information, and so we had to store it in some general purpose register. RIP, of course, that has a purpose. That's the entire reason this program runs. It is constantly keeping track of which instruction where we are running at the moment. And so that's constantly keeping track of it, which, lo and behold, a instruction set architecture usually needs some way to keep track of what instruction it's executing, which, come to find out, there is an instruction pointer of sorts inside the Yan85 code. And we'll explore more of that in a second. But
wait, doesn't every architecture have an instruction pointer?
It should. But, there might be a case where it doesn't. And it's simulated in another way, where instead of having a discrete value that's an instruction pointer, it's more of like the next instruction is derived based on something else.
Okay.
Yeah. But normally, like, for most ISAs that are like generated for actual computer use and not for a CTF, they will normally have a instruction pointer to just, keep track of where we're going. And this is all stored in the same place. All these registers are stored in a register area because this is 64-bit. But if we imagine this was 32-bit instead, all the registers in 32-bit are stored in the same place that we have our memory and all our instructions and stuff. So this is cool. And they're in like larger sections, of course, but think of like that idea, but now it's smaller because now we have a more finite space that's not just really huge. I mean, we could make this really huge, and even if it was really huge, we can still make that same, not necessarily assumption, but same understanding of it. It's located in the same chunk of memory, and same chunk of memory space. And that's the same thing for Yan85. So we have some registers here, which when we run, say, baby key, if we run baby rev 14 teaching, we can see that there's some, from the verbosity of what's going on here, we can kind of make some assumptions of what each of these are meaning. So like V might be telling it some verbose output, and I is referencing some instruction. And then S would be some call it's doing, some instruction interpretation and output, which is more of looking at this and noticing that it's outputting what the instruction is doing. So, but what's nice too is we can actually see what what registers are here, because these registers are constantly being toyed with. So we have some IMM instruction, and it looks like it says C equals 0x96. It sets that equal to C. So C now equals 0x96. So we can then say, all right, our registers are consistent of A, B, C, D, S, I, F. This is the general structure that your memory and the area that you're going to be loading things into is consisting of in Yan code. This is important because if you start writing things to the memory section, if you start overwriting then over the registers, and then past that is like the exit for the program, you've now exploited or overwritten the return address and now crashed the program, which is important for 4 and 5. And 6 and 7, but 4 and 5 are more discreetly like that's what you're doing. So that's the general structure of how this is laid out. Now what is left here is, so we've figured out our memory, or at least how that's laid out. We've figured out our registers. So now what instructions do we have? Well, the instructions are going to be something we need to figure out with like Binary Ninja. We can, from the teaching, we can kind of make sense of like what instructions are there, but what if it doesn't have every instruction that we could potentially run? So let's go see what they have. So we'll go to Binary Ninja here. We see there is some interpret, and then there's interpret instruction. So cool. There's an entire function that is just dedicated to interpreting our instructions. So that's perfect, which means that this should technically have every single instruction that we would want to run. Now, all the emulators for all the challenges will have the same structure. They're going to have some loop that's going to be referencing every single instruction. And then for every like sub loop, it might have like, if it's add, it's going to carry out that function and then leave. Every challenge that's Yan85 related is going to have that if it uses this interpreter. There might be slight differences, especially for the pwn. They had to include some vulnerabilities, but if anything, they're very slight, and they're not going to be like completely mind changing to where when it's added in, it completely changes how this thing operates. It will not be that at all. So what's cool here is we know then that our instructions are, let's see, we have IMM, we have add. We obviously know, we can pretty much conclude what add does. And if you remember how add works in x86 add, it takes, if I have add register A plus register B, it'll take that value of A plus B and store it into A. It does the same thing here. STK, which might look like stack, and we'll come to find out later that's probably referencing a push, like you can push and pop to the stack. And then STM is a set memory. So you can, like we were saying, mem copy, we would set the memory somehow to a certain space. How that's referenced, I can explain in a second too. LDM, so we have STM, which might stand for set memory. LDM is load memory. So this is like load effective address, if you've used that before in x86. So we're loading from some reference. We're saying, okay, this address, we're going to load from there and grab the value that's at that point. Compare, or CMP, that's pretty obvious. We compare, and then some result gets generated. And then jump, it'll jump to some other place in the program's execution. And then interpret sys. Sys is going to probably reference what we were talking about before, syscalls. So yep. This is call instruction. Perfect.
So with this, are you just like guessing, or guessing that that's what they mean, or you already did the research into it and already know that?
I have already done that. But
Okay.
so I'm just trying to save the time of like explaining. But
Yeah.
if
I
we
get
want
that,
to,
but
for example, STM. What the fuck does STM do? I have no
yeah.
clue. So we go to STM and maybe we look at, okay, so well, this is obviously an artifact of the teaching binary. I'm gonna ignore these, but these are the instructions that are actually for the program. So we see that it reads a register of some value and then stores that value there. Because if we go look at the read register, if we just take one of these values, what it does is it says, okay, I'm going to take some argument, parse basically it's a giant switch case based on that argument, go to here, and then if that value, like if this was a valid switch, I'm going to say, all right, dereference the value. So whenever you dereference a value at some offset, so like it's doing here, this is probably some argument that's at a point of arg1 plus 0x3fc. So it's going to take that value at that point, and it's going to basically give you that value, not the address, but the value that's at that address. So then that's going to be stored in RAX7, and then that's going to be returned. So right away we know it's saying, all right, this point in memory, grab the value that's there, bring that back, and we just store that into this value, this RBX1. Then we say, all right, we want to read a register. So we want to read another value at some point, which is, so if I have some register A and it has a reference to another memory segment, I'm going to say, give me that value in that memory segment. And then I'm going to do the write memory command, which write memory, if we go look at that, takes two arguments. Well, it takes three, but this is the memory space that we're talking about. It takes two arguments, arg2 and arg3, one of which it's going to figure out first what that value is, and then it's going to use that as the place to write the memory, or write that value that we passed in to. So this, what it looks like, how you could probably represent this. Oh. So, actually, yeah, let's start breaking down the instructions. We'll just start breaking that down pretty.
Yeah.
Sorry, because it's probably not making too much sense right now. I'm just going off. Let's start writing down what these are. So I'm going to go from the interpreter loop here, and I'm going to just start copying what each of those are. So we have IMM, we have ADD, add, we have STK, STM. These are all prefixed by interpret underscore, but I'm just dropping that part off. LDM, and then CMP, JMP, and sys. So cool. IMM, if we look at this, so IMM looks like it will take an argument too. So the way this is also represented, by the way, we have this byte that's passed in right here, this arg2. If you remember, arg1 is going to be our memory space, and then arg2 is going to be consistent of the other bytes of our, or it's going to be consistent of our instruction. So this is going to have 3 bytes, and I can prove this here in a second. When we look at the interpreter loop, the value that we pass in as the second value is basically a conglomeration of some reference within the memory, which is just plus 0x41, which is significantly smaller than the rest of the stuff in the program. So remember how we were saying our instructions are at the beginning?
Mm-hmm.
And it's going to parse that and then throw that as the second argument. It does some funky shifting to it to basically make sure it's only grabbing that one 3-byte value. But it's always 3 bytes. And when you copy this in, it doesn't actually do that here. But the moment you start looking at how these instructions are actually being parsed, like for example here, it grabs the second byte of arg2. And then it parses, or it switches based on that. So if the second bit is ANDed with 0x10 equals 0, or if it doesn't equal 0, which means that it was meant to be that instruction, it would interpret the add. Then those 3 bytes get passed to interpret add. Now interpret add says, all right, I'm going to grab my arg1, or sorry, I'm going to grab my arg1 here, which is my memory, and then I'm going to say, all right, arg2 bit 1, or it's not bit, but byte 1, I'm going to then figure out what the value is at that register location, or whatever like this value, like this, say this was 0x20. Whatever register 0x20 is, it's going to then read the value from that, store it here. And then it's going to read the value from 0x, whoa, go back, 0x, or sorry, arg2 byte 0. And then it's going to read the register there, add it to, because we have an add right here, which is rbx1, which is from this last value that we grabbed. It's going to add it to to that register arg2 0. It's going to figure out what that value was, add those two together, and then write that back at the register that we referenced in arg1, or for the byte 1. And this is just how we construct the instructions, which I'll also go into more of, like I'll double back on this, but I'm just trying to prove here basically that there's 3 bytes for each instruction. Yep. And that's the reason why this is important, is when we start looking at the interpret instruction here and something like IMM. The IMM is doing some interesting things where we are grabbing the byte 0 and the byte 1, or we're grabbing the byte 0, whatever that value is, and we're doing a write register to byte 1. But it's the value that byte 1 is representing. And when we go to write register here, this is where we start parsing through what each register is representing. So like, for example, whatever the value that this register is, display as, we'll do 10 decimal, this 1020, it's going to then apply, it's going to say, all right, well, we're going to write the value that we passed in to that register value. Now, what is 1020? I have no clue at the moment. We can kind of get some guesstimation values, though, from the teaching, which is really helpful. So when we start looking at, say, our interpreter loop, our interpret instruction, it prints out...
You're looking for 1020?
Yes, that's like, yeah. So we're looking for this 1020 value, which is right here. We're looking for, it says A, B, C, D, and so on. We have arg plus 1020, 3FD, 3FE, 3FF, and so on. And those are referencing A through F. And if you would like, what I did, which helped, was we can start...
and A through F is our registers.
Yes, exactly. And this is helpful to kind of probably lay this out too. So when we start trying to figure out what each of these is looking like in memory, we may, in some of the instructions, reference these directly instead of, using write or read register instead. So this might be helpful to figure that out. And these will always be the same, by the way. So these will always be, starting at 1020 and then all the way to, I think it's 1027, 1026, I think it comes out to. What is this? Display as, 1026. So it goes all the way to 1026. And that just makes sense. It's 1021, and then 1022, 1023, 1024, 25, 26. Cool. So whenever we see a value that's like arg1, remember, that's our memory space. So that's the base of our memory. And then we're going to add like 1021 to it. That's referencing specifically register B. Does that make sense?
Yes, because it's at 1021 and then arg1 is our memory space, which now we know it's these 1020 to 1026.
Yep, and so this makes more sense now when you look at like interpret or you look at this write register function, and you see 0x40 is switching to write to RAX6, which was arg1 plus 1020. So now we know that this write register function is writing to registers. It's kind of obvious just from the name, but now we know specifically which registers it's writing to.
Which is S. Or 1020 is A.
Yep, correctly. And if we look at, say, like here, what is this guy? Well, I don't know. It's 1026. So this means case 1, whenever there's a 1 that's referenced in the instruction, it's referencing plus 1026, which should be F. So this is really nice because we can go through and then figure out, for later on when we start building out an assembler, how to actually assemble these instructions. whenever we want to write a specific value there. So the IMM guy, if we write out the steps, we said, all right, this is assign some value to some register. And this would look probably like C equals 34, something like that. The instruction would look more like this, though. So it would look more like that. And C, of course, would have to be represented by a byte. And that's just from what we saw whenever we are looking at the interpret IMM. The arg2 value that gets passed here. So arg2 byte 1 should be our argument 1. And the only reason why we can assume this is because when we go to write register, this is the value that it's using to parse what register it should be assigning. And just looking at how the IMM instruction should be structured, well, this makes sense that that should be arg1. That's just how I'm making that assumption to there. And then arg2 0 is going to be the second argument that's passed in. And that should be the value that gets assigned there. When we go to write register, it's whenever we start assigning arg3, or var18 in this case. When we look over here, var18 is what's being assigned to arg1 plus 1020. So we can make then the assumption that this is how the instruction looks. And that's good. I feel like this instruction is fairly straightforward. Same with add here. So we add two numbers and store in first register. So this would be like A equals A plus B. So that same syntax we were talking about before. And then if we want to look at actually how this instruction is set up, say interpret add. So like we were saying before, it reads register value, and then it'll go ahead and add that to some value that it reads from the other register, and then store that in register 1. So, or in arg2 byte 1. So we already kind of agreed that this was the argument 1. So since this is the argument 1 value, this should be the value that we're expecting the addition or the sum to be put into. So when we think of how this instruction should look, we'd say add, I'll say A, B. So it'll take whatever is in B, whatever is in A, add them together, store them in A. Cool. Now stack. What the fuck is STK? So just to prove that it is stack, let's look at what the hell this thing is doing. Interpret stack, or STK. So just right off the bat, it says pushing and popping, which sounds straight up like stack operations. So just
you relied on the hint or the straight up teaching to know that just is a stack?
No, this is also in the, let's go look at the testing one real quick. Because I believe the testing one also has this. It'll spit out basically that this is, it'll say it's pushing or popping. So if we look at that, so we'll go here and we'll go to the interprets. This one. Sorry, it moved it over for some reason. Oh fuck, maybe I apologize. Yeah, I was wrong. But yes. So then I did. I used the teaching one to figure out which one was pushing, which one was popping. But you can also kind of assume then, you not assume, but you can also investigate it for yourself too. And the reason why I say that is because it'll take some value 0x400, which again, what is this? This is a 1024. So we know that that's a address referring to, I think it's D. It's either C or D if I remember correctly. S. Sorry, S. So S, which coincidentally is the first letter of stack, it takes the value there, adds 1 to it, stores it back there after adding 1 to it, and then it'll take some whatever value you brought that you passed in, so arg2, whatever the byte is at byte 0, and then it'll read the value of that register that you are trying to reference, and then store that into memory. So this, just recap that again. I have some value in A, and I'll say basically stack push A, and it'll push whatever values in A to the stack. Kind of like what we do normally. We normally can push like 2 or something to the stack, but you might do something like instead add 3 to RAX and then push RAX. So that's kind of what's going on here. And we see then on this function, on this part of it, that this actually takes the value that's in the S register. It will use it to reference some value in memory. Notice that this is write memory, not write register anymore. If you look at this, nothing like write register. We're not trying to parse it any fancy way, but we do offset it by, I think this is 765, I want to say. Yeah, we offset it by 765 plus whatever value gets passed into arg2, which when we go back and we look at arg2, so this is 0, this is 2, it passes in S. Whatever the value of S is, it passes into this memory function. And then inside the memory function, it uses that to reference a spot in memory. And it offsets by 765. And this is just because, it can't keep everything in the same spot in memory. It has to, organize it by some way. So when we use this RAX2, we've now offset some part in memory, and then we assign the third argument to it, which arg3, remember, is the value that we passed in as the byte 0, or the register value of the register that we referenced with byte 0. So
okay, so like in 32-bit, you would offset by 4 bytes, but in Yan85, it's 722.
Well, so the reason for this. Don't want my arrow key there. I want my arrow key here. So you have your instructions. This, we'll say this is like 0, and this is 765.
Mm-hmm.
It's like it's that. That's the reason
okay.
why. So you take the base
sense.
of it, you add 765, and then add whatever offset so that it then puts it in memory somewhere.
Right. So it doesn't write in the other parts of memory that's allocated for other stuff.
Exactly. So you don't start overwriting code, and you don't overwrite anything you've already written to memory. And this is also why this variable, this S variable, is being used. It's incrementing each time you put something in memory, so it moves actually to the next spot. So whatever it was, or initially, it'll add 1 to it, and then put your memory, or whatever your value you're trying to put in memory there, and put it in that location. And then, in this one, it'll grab whatever the current value of S is, read that memory segment, figure out what's there currently, and then assign it to some register that you've passed in. So we said, okay, in our argument 1 value, so arg2 byte 1, we passed in whatever the representation was for register A, and it'll run the write register function to write whatever that value was in memory to register A. Then it'll take the S value. For some reason, it reassigned it again. No clue why, and then it'll go ahead and take that value, subtract 1 from it, so it goes back down, and then assigns it to S again. So without using these printf function or printfs to figure out which one's pushing, which one's popping, we can already start seeing that there is some mechanism of growing and shrinking, which is exactly what a stack does. So whenever I want to push to the stack, I increase my stack pointer and I write some value there. If I want to pop from the stack, I grab the value from the stack and decrease my stack pointer. So it keeps increasing and decreasing depending on what you're doing. So this is super helpful, or super useful. It may or may not be helpful, but it's super useful to understand this because this instruction is how you're going to store things on the stack, and how you store things in memory using a stack instruction. So this would say push A or pop A. So it looks something like that. That's kind of like the logic behind it, and how we normally do most instructions, right? We usually push or pop. So then this would say, all right, well, we would logically be like A equals 4, push A, So now some memory offset of whatever arg1 was plus, some value that we put here. We'll say it's like offset plus 765 equals 4. And actually this offset would be our S, right? It'd be our S value, our S register. And we can also start labeling maybe here what the important things are. This is stack pointer.
Okay. So is the point of doing this like just basically forcing you to understand computer architecture more and realize that it's very similar regardless of...
Yeah, I mean it may not be the purpose of it, but like doing this, it's all the same. Like a Turing complete language is going to have similar ideologies between everything. So, whether you like, what was it for one of the CTFs recently, there was an entire game written in sprintf, and that was because sprintf is apparently Turing complete. You can write an entire working program using sprintf or emojis, funnily enough. So this is just to have this concept of like you can write a instruction set architecture in like pretty much anything that
right.
Well, not anything, but
virtually anything.
Yeah, virtually anything that has this ability to procedurally execute, do arithmetic operations, and do some function for you, which is really nice.
Yeah, that's what the biggest thing I just got from all this. That's why I'm asking, like, oh, so this is the point why Mika is learning this. Is it solidifies that you understand computer architecture, and then that you could easily translate it to like something else that's Turing complete.
Mm-hmm. Yeah, and like this is where when you start like going through this program, and why I'm saying like I can kind of assume an instruction does this or does this is because it's the same functionality. That's all it is. So the stack, this push pop, it's the semantics are going to be different. As add is obviously not maybe always this, or IMM is not a valid instruction in x86, but the concept is the same. Usually this is probably like move, so you move C34.
Right. Yeah.
So
that's what I'm getting from what you just went over is okay. That's why we're doing this, because it's solidifying that every computer architecture is the same in a sense, and you can do stuff like this. Okay.
Yeah.
Makes perfect sense now.
I'm gonna exit out this too.
It's just the method to the madness.
Exactly. Just trying to figure out what it exactly is doing to understand. You got to understand how the emulator's working, basically. So we can. So yeah. Then this right here. So stack, and we want to figure out then. All right. Well, is this doing push or pop? How is that referencing push or pop? Which values does it use even? So it checks actually if argument 2 is equal to 0. And if it is, it'll push. If it's not, it'll push. But if it is, it looks like it will pop. Yeah, so then it grabs argument 1 and then checks if it's equal to 0 or not. And if it's not, then it'll go ahead and pop. So what that looks like is hello. Okay, R2. So we say 0 A. So this is push A, and then STK A0 pop A. And that should be all for what that instruction does.
Oh, okay, that's so cool. So that's why it's checking for 0, and then you're just using 0 to determine if it wants to push or pop.
Exactly. And this is 3 bytes. So STK is 1 byte, 0 is another byte, and then whatever is referencing A is another byte.
Okay.
Yep.
That's cool.
Now I'm gonna do the rest of these. STM, I would say honestly, let's see, compare. Yeah, that's pretty important, I guess. Sure, we'll just keep going through this. So STM is, it's obviously doesn't sound like an instruction that we've used maybe in x86. So let's go maybe see what that is. So right away, like we were talking about before, we can see that it's reading a register from argument 2, and it's putting it into this value, and then it's reading the register value from argument 1, whatever register that's referring to, and then putting that as so whatever value is in register, whatever value is in the register that argument 1 is referring to, it's then going to reference that point in memory and assign the value of whatever we passed into argument 2, whatever value is in the register that argument 2 is referencing now, into that spot in memory. It's kind of convoluted. Not too convoluted though, but we already know what the write memory function does. We already were looking at this. It's a similar thing, because this S for here is not the same. Just remember, like when we were writing to the stack, we were passing in the S. So this is just whatever your argument 2 is here, or your argument 1, I guess, technically. So when we jump back here, we see that it passes that reference value. So whatever we get from register 2, so say we got say we passed in a reference to B, and B was equal to 5. It'll say, all right, write memory, we'll pass the memory buffer at the index of byte 5, and we'll write the value of, say we said 2, because 2 was in register A. Does that make sense?
A little convoluted. Maybe once I see your example.
Yeah, no, sorry. Here. So set memory value referenced by register to value referenced by other register. And what this looks like is you say, okay, so some memory address of, so arg1, which was our base, and then we add, we'll say some offset, which, what? Actually, I'll figure out this offset here. So we'll say our offset, we'll say A is equal to 0x23, okay? And then we'll say, then the offset here would be arg1 plus A. So we just dereferenced it, right? So now we're bringing in the value that's at A. We add 765 to it. We say that's equal to, we'll also add here, B equals 0x44. The dereferenced value of B. Does that make sense right there? Actually, let me double check that real quick.
Wait, I was like, wait. Okay,
Hold
yeah.
on. Yep, that's right. So we'll walk back through this again. Remember, this is how we reference some spot in memory.
Yep, because we're jumping to that spot that we're allowed to actually write to.
Yep, so the base plus 765 plus whatever our offset is. Now remember the idea of dereferencing? So that's what we're doing.
Taking the value that's in the location, not the address.
Correct. And so we also do the same thing with B. So what this ends up being then is, say this is 0 plus 0x23 plus 765 equals 0x44.
The new address, or the new value at B.
Yep. This would be the new value at whatever this equals that. And this right here, I'm just assigning 2 variables. I can actually split this up if you'd like, if that looks better. So we can make it look like that. And this is just a basic, I want to set this part in memory to this. This would be also probably similar to like a move instruction, or a storing instruction. Does that make sense?
Yes.
Okay. Now the syntax looks like STM, and you would say A, B. It's pretty simple. Double check here. We'll look. So this instruction is doing all the work. It's going to write a memory for whatever register we passed in to the value of the second value that we passed in at that register. Because this is byte 0 and this guy is byte 1. So right away we can tell that this was argument 2, this was argument 1 for here. So we can order our syntax like that. We can say STM-A and then B. So this will basically do what we just set up above here. Now, if you wanted to say, actually do what we just did, this A, B, you would do something like this, where you would do IMM, because remember we just talked about immediate. We'll say A, 0x23, and then IMM B, 0x44, and then STM-A, B. So look like that.
Right, because you had to set, or because IMM is basically like a move instruction, we had to set those values first.
Yep. It's setting those register values specifically to, well, 0x23 and 0x44. Good so far?
Yep, and then STM just sets.
Yep.
the
And
VB.
then LDM is kind of the opposite of it. So it loads some segment in memory. So this should be fairly easier to explain if you understand what STM does. So we go to LDM. It's very similar in size. So we read the argument at the second argument, and we read the memory that that's referencing. So we dereference that value, read the memory that's at that location, and then we write to the register referenced by argument 1. Pretty simple, right?
Right, so yeah.
Okay.
So whatever you pass in is getting written.
So we read from mem, store in reg. So we'll say, looks like LD, or actually, it would be something like, we'll say B, or, yeah, okay.
So B would be 0x23 from the from STM.
Yeah, it would be like this, arg1 plus A, for example, plus 765. And this would mean that B is now equal to whatever the value is at that location. Like if you ever reference B, it's going to have the same value. This is more of like my shitty C representation of it. So
Yeah, it makes sense when you're talking it out. So
yeah, okay, good. I'm glad. So we'll say LDM A, B. And so the B, this is actually wrong representation. Should be the other way.
yeah, I
around
was
for
about to
this.
say,
Yeah.
it's the other way around. Because
And what's actually, and I take that back. It's not, for talking about this technically with it, it's only dereferencing the second argument, not the first one technically. So if anything, it's doing this, which would mean this guy is doing that, which actually makes more sense because we don't dereference the other value. We just grab the value that's at the location, and then we store it at the dereferenced value for the first argument. Then we dereference the argument here to store that into B. So now B will equal whatever the value is, not the reference there. So same thing as we were talking about before. I just didn't have the right representation. That was my fault. Yeah, so those are pretty
the big concept still makes sense. I mean,
yeah,
like, the big idea still makes sense.
The same concept is the same. It's just I failed to represent it right. So compare, without trying to look at what it does, we can already kind of say like compares two values. And then right away we'll say if A, I don't know, and then some bool B, then C, right?
Yep.
So if we look at this, go to compare, there are a bunch of switches here.
Yeah, but because this one doesn't have a jump not equal, jump if equal. So we have to do a compare, and then we could do a jump instruction afterwards instead.
Precisely. Now, here's what's a cool thing too. What is this guy right here? We'll go ahead and display this. This is 1026. Same here. This is 1026. So it starts
Which is
out
register F.
Register F, correct. It starts out the function by setting it to 0 first. Then after some whatever switch case, whatever it succeeds, it'll do some quick maths and set that current register value, ORed with whatever value, and then set that at that spot. So it'll keep doing that. Now notice this is not an exclusive switch case. This is a continual. So there'll be one after another if statements that will hit. Now, we'll say, all right, so like say it gets 0x1, 0, and 8. So then it'll set that and return with some RAX value, but that value is not important. This register has now been changed. It's now been modified. This F register has been modified. Now, see if I can find a good way to show this, actually. We'll go to, I think Baby Pwn will more than likely have something like this. Actually, no, actually, we'll do baby to baby key. So we'll GDB baby rev 14, and then disass main. Do I have any jumps or compares in here?
No. Oh, there's jump equals, which is 265.
I need a compare, I guess, is what I'm looking for. Disass interpret instruction. This one will definitely have a compare, I would hope. It has a bunch of tests. My life is a lie. Okay, anyway, I'll just explain this because I don't feel like hunting for it. Compare instructions in x86 and in this instruction set architecture have a way, how do you represent that something succeeded? Because if I compare, so I compare two values, where's that value stored? Of like, if I compare A and B, if you remember like to any of your in assembly that you've ever seen from GDB, when it does a compare, there's never like if compare equals this. It just says compare, and then it'll do a jump of some type. But if it's like jump not 0, how does it tell, like, what is it not 0? Like, what is not 0? Obviously you could say, okay, well, of course, if it's jump less than. I think that's a better example, actually. So you have two values, and obviously, if A is less than B, it'll jump. That makes sense. But how does it store that value? Where is it stored at? Like, it's not just like
a specific register for that.
There is. It's not just like ambiguously like in the air for whatever reason. It's not just like floating there. So when you look, you have this flags, E flags. There's a set of flags that are set here, which actually those may not be the flags directly. I think they are, but there's this concept of flags, right? So the flags will represent what an outcome of something, whether that's an error, a compare, or it needs to basically say like, hey, this was the result of this, but it didn't necessarily store it in like RAX, for example, because it wasn't a subroutine. So the registers that you're going to see are flags, but the flag here, like, it doesn't say flag, but it sounds like F, right?
Yeah.
Yeah. So,
yeah, it was set in F, which is 1026.
Right. So compare, if it does the value and it puts the flags there, then it probably does the same thing for Yan code. And that's, we can kind of see that here. It puts it into 1026, which is F, and it'll just keep ORing this, so it keeps changing it based on how many of these statements is true. So if we just look at some of these statements, so if var A is greater than var 9, okay, if var A is equal to var 9, and then we can, or if it doesn't equal var 9, we can just keep going through these and checking like what are these statements, and they will mutate basically how this flag looks towards the end. As far as exploitation, jump and compare you probably won't need a ton. If you ever go back and do these problems, jump and compare are going to be very useful to understand how a program is checking what the key is. So when you're trying to figure out what key is it expecting, well, it compared A, which A was recently loaded with a 0x42, so it should be a capital B there. So just for later when you're walking through these, if you're doing the baby keys.
But we're not doing the exploits for that, or we're not using them to exploit it as much as we would think.
You can, like, you can if you want, considering like if say I want to iterate over a bunch of instructions, but I don't want to, write out that many instructions, I can write a loop in Yan code, and that perfectly is doable. You would say, like you would in assembly, you enter in a function, and if a condition is not met, then you just jump back a few instructions. So it's you can. I'm not saying you shouldn't. I'm just saying that I never needed to.
Okay. Cool.
So right away, a compare, and without going back and forth on this, we use the same logic of how we try to figure out what the other instructions, like how the arguments and syntax flowed. So we check and see which one has the byte 1, which one has the byte 0, and because we identified those as our arg1 and then our arg2. And so we would say, okay, this is compare A, B, right? So if A, then B. And this will modify F, reg. So we can go here to our F register. We'll just identify that. We'll say this is our flags. Now, we'll say jump. Well, we kind of know jump already. It's going to jump to some different spot in the program. We already haven't really identified what our instruction pointer is. We can probably assume at this point, if a lot of these are like representative of maybe what the x86 equivalent is, we can probably see that I is probably the instruction pointer. But if we wanted more solidification of that, or solidifying of that idea, we go to the jump instruction, and when you reference how x86 works, jump normally modifies your instruction pointer. It says the next instruction you're going to execute is at this spot in memory, and it'll change that, and the instruction pointer is like cool, and just goes with it and starts executing. So here right away we can see taken and not taken. So this is this idea of branches in like computer memory, which is an if statement, is effectively what that is. And if we notice too, we'll say display as 1026, it uses the F register to decide how it jumps. So if the argument that you passed in to jump, the arg1 and then I think arg0 is milling about here somewhere. Yeah, right here. Right here is arg0. We basically will use arg1 along with the F register to figure out how we jump. And that's because that's the, like, if you want to say jump not 0 or jump less than or jump greater than, that's what the arg1 is representing basically. And then arg2 is this value, which is representing, like, if I want to jump somewhere else in memory. Right away, we see there's a different little register here, which is 1025. And 1025 is what? I. So just double checking real quick. If our jump is taken, then it reads a register at whatever we referred to in arg2 and changes I to that. So if, we say, okay, I want this to jump back to instruction 2, I will say, I will do IMMA equals 2, or IMMA2, and then that means A is now equal to 2. And then if I want to say, all right, jump, and then I'll say if it's, less than or something, and then I'll put A after that, which means if it's less than, it'll just jump back to whatever the value that's an A. And then it'll reset 1025, which is I, to whatever that value is. So looking at this, it's just simply like this. So we say jump to some other place in execution. And this is like jump to or something. Or so we can be a little bit more specific probably. We can say jump if greater than. Say jump to 2 if greater than. And then that would look something maybe like JMP is the proper syntax for it. We'd say, I actually don't know what the specific flag for the greater than is off the top of my head, so I'm just going to use tube as a representation. Actually, that might be bad because of how this is looking. So I'll say jump 4 is A, where actually we might do something and do IMM, A is 2, and then we'll say jump, and then this would be like if greater than, jump to whatever the value at A is. Does that make sense?
Wait. So you're saying A equals to 2,
Mm-hmm.
and then it. Wait. So what's the So the 4 you're just using for now to check if it's greater than, right?
Yeah. So there we go. 4 equals greater than number. So this is the greater than representation, because remember when we were looking at the flags, whatever math goes on here. So this would be like, so effectively, if your F register, your flags registered as or equaled 4, and so if you look at that, just look at the logic here basically. So I said some value, say 4, and then it says if 4 equals 0, or 4 doesn't equal 0, or wait, yeah, if 4 equals 0, or 4 doesn't equal 0, and so basically we're just trying to check right here. Yeah, okay. So if it equals 0, or if 4 doesn't equal 0, and so like this is all one statement right here.
Right.
This is what's going on. And then and this register bitwise anded with that first argument doesn't equal 0, which means that is a valid either it's supposed to be greater than. So in our case, like we were checking if the compare, it should be greater than. If that ands correctly and we get a 4 back, then it's a non-zero number. It will go ahead and it'll be taken. Otherwise, if say that value failed, say like we had compared the two and the bits that got set in the flags was like less than or 0 or something, then this would fail out completely, which would invalidate this, which would mean that this would also invalidate because R1 wasn't 0, but this also failed. So it would just go to this segment right here, which would say it's not taken, and it would just drop out. Because, yeah. So does that make sense?
Yeah, it's just a really complicated check.
It's just, yeah, it's the way it's doing that is more of just, it keeps the where I have to store of how my comparisons are to like a minimal, and it's just because you have to use a F register. So it's nice because you already know what that F register should have in it if it is greater than. And if it is greater than, the compares will set it up to be a specific number. Well, you know that specific number, so then just compare it against it, just bitwise and it. And if it ands out to a non-zero number, then you know it's correctly succeeded. It should be at least equal to, maybe at least equal to or at least less than. Like, especially if it's less than, it might be like less than or equal to. Well, if it is equal to, it will instead just be equal to. Like, so you kind of can know like how it might predict, what that's going to be. Just from this little equation right here. I hope that part at least makes some sense.
Yeah.
Okay. So then...
Yeah, it's just like any other jump instruction except here we're using the F register.
Yep. I mean, we would be that same logic actually happens here in
right.
in the x86.
Except it'll be E flags.
Yeah, it has all these other flags and stuff, but the jump instruction kind of does a similar thing. So when you do like jump greater than, it basically checks and seeing, I think it has separate flags for each one, but let's say in the concept that it has only one register for it, it would be the similar concept. It would say, all right, well, jump less than is only going to check for this byte in this register. And if it doesn't exist, then, don't do it, of course.
Right.
So then sys right here, this is going to be an important one for 5, 6, and 7. So the register value, not the register value, the instruction value is just sys, which syscall, we can kind of assume that by now. And just by looking through this, we can see this one is open. If we're just looking at like the teaching one, open, read code, read memory. And I think the teaching one, using that for this is actually really useful because you start to kind of understand like what these should do. And it's an important distinction because you have write register and then write memory. Sorry. So you have read code and you have read memory, but they both do a write register. And that's why that's like, I feel like important because the slight distinction is one says, let's see, where is it at? This one reads from this value plus 0xf3fc, which is fine. But the way it offsets, one of these adds and the other one multiplies. And I think this one multiplies, if I remember correctly, when it reads code. it will multiply by 3. I forget at which point it does. Let's see. Code plus that, it bit shifts it, which might be actually the reason of what it's doing. So yeah, I think this is having the same effect. Let's see, is this 765? Yep. So this adds 765 after it shifts it over. So this one add, it would do basically some manipulation to the value there, and then it'll apply the write register function based on this if statement. And then the read memory one instead just adds, let's see, so it'll grab these two values, which are B and C, and then it'll apply this function to it, which it'll use the buffer of arg1 plus 765 plus, so this was our memory base. Add 765 to it, and then add another value, which is inside B. This one, on the other hand, I totally missed it. I apologize. So right here, this is the part I was talking about, that it times is 3, because I'm used to IDA's output. IDA makes it a little cleaner, but here for some reason it did it just 3 times. So what it does is it takes the argument value. So when it reads code, it'll take whatever RDX6, which is resolved from your, let me look here. It's resolved from your B register. So, and then it'll take that, times it by 3, and use that as the offset. So now we're some memory and code. Remember, before we added 765 and then did some stuff to it, this time we're just multiplying by 3. So it's very possible that we might overwrite like actual instructions with this. Whereas this guy, this read memory guy, it takes the base, adds 765, and then adds whatever value that's in B, which technically should be able to go higher. And the reason this part is very important for the exploit part, because let's look at, I just want to point this out real quick. We did 3 times, I'm going to say so right off the bat, each of these values, these register values, can be only at max 1 byte. So that means your maximum value is 0xFF, which is 255. Okay?
Mm-hmm.
So the maximum value there is 765. So that's
our spawn memory.
Yeah, that's right on the cusp of the memory, which means you can't go past that. But we'll say whatever our base is, we'll say 765. So we'll say 0xFF, which is 255, plus 765 is 1020. So we can go far beyond that. And so that's what this guy, the reason why this is important. You pass 0xFF right here. So this is like register B. So you set B to 0xFF. You add 765 to it. You're now in like the very end part of the buffer, basically, the memory buffer. And then here, this is n bytes, so the number of bytes you want to read, which is defined, so this is RDX9, which is defined up here by 0x21.
Which is B.
Which is B as well. Why should be actually C?
22 is C, yes. 1022 is C.
Yes, but am I just, what the fuck?
Yeah.
Hold on.
Wait,
So 0x48. Oh, that's funny. I was like, I know I'm not crazy here. It does some weird math right here where it might reset whatever this value is. So if RAX9 is greater than RAX48, it'll do this math, which is why it sets it to that for whatever reason. That's just some weird protection it does just to make sure that it's at most 0xFF. But regardless, so you set it to 0xFF, and then this means that you say 1020. Well, now you can write an extra 255 bytes, and now you've written from 1020 to 1020 or 1275, and that's more than enough to overwrite a bunch of shit in the memory. So just keep that in mind. This instruction is very important for that. But anyway, we keep going through here. So we have sleep. We can also see that there's an exit one. And we don't even have to, necessarily look at the print statements. We can straight up just see the syscall, or the C call. It's not even a syscall at this point. It's right now it's a libc function at the moment. So we have write, read, and then open. Open, you can probably assume, is to open a file pointer. And then you could read from that file pointer into memory, and then write to standard out. So this would be how you might open a flag if you were to use shellcode. But if you don't have the open syscall, maybe you can't do that, which would be a total bummer and totally what 4, 5, 6, and 7 do to you. But in 14, 15, 16, 17, 18 of the baby key, you have every single syscall that you need. And that's the concept you want to do. You want to be able to use this shellcode. Like, you can use the same shellcode for all the ones that are like, give me shellcode, which I think is like 16 and on. And you basically are just going through this the way you would do x86 syscalls. I want to open, I want to read into memory, and then I want to write to standard out from that point in memory. And all these values, so like write and read all take different, values. Like if I want to write to standard out, we can open up like the man page for write. This is where you start crossing the lines of like the difference between or how the emulator kind of crosses paths with how C works, or how the C program's actually operating. So you man open. And you can see that you need, or I guess you wouldn't want this one, but you want this guy. So you look at open here, and you want the first value to have the file name, and then the flags. And then if you want to read, you would say a file descriptor, and then a buff. And if you want to write, you would also say a file descriptor and the buff. Well, here, if we want to write, I would write to some file descriptor, which really, really nicely, Binary Ninja also lays out these terms for you, which is really nice.
Right, yep, file FD buff. Yep. And bytes.
Super helpful, because, if you don't want to look up the man pages. But this means then, if you look at, let's say, like, the decimal right here, this value is A.
Which is A, yeah.
Yeah, so A needs to have whatever file descriptor you want to write to. So you just, put 0 and A, and now you're writing to standard in for whatever reason. So you might want to change that to a 1 so you can write to standard out. And that would be, we use IMM instruction, set A to 1, and then we just, set all the other registers, and then we just call it.
And then you can write out the flag.
Precisely. You were right on that. Because you just give it a pointer, right? So you give it to whatever value is referencing that point in memory. And remember, strings are null terminated. So if you just say write to standard out at this buffer address, this many bytes, well, let's look back here. The value it uses for the buffer, so it's the base of the memory, adds, I think this is another 765, yep, and then it adds whatever value's here, which is B. So you just give it the address to there, and right off the bat, you can just read out the flag. You don't need to like do a bunch of jumps. You don't need to keep going over it. You can just say, here's the point in memory, go print it out. And funnily enough, if you store this value in the stack, it's just whatever the stack pointer is. So, or the stack pointer minus some value potentially, or the stack. You can play with it to figure out which one it is. But it would print it out for you until the next null byte, which is going to be, probably at the end of that value, considering most of this is going to be wiped out initially. So there's going to be all zeros. But if you don't want to assume that, you can always set a null byte if you'd like. So call, syscall x. So syscalls we have are exit, read mem, read reg, or no, not read reg, read code, write, open, sleep. I think that's it. Read mem, read code. Yep, and then open. Cool. Now, these will be decided upon by your first argument. I'll double check this here. So this if statement is looking at the first argument, or what we identified as the first argument. Now, the structure of your jumps, your compares, basically all these functions, like I said before, they're all the same. The only changes are going to be your operand order, so the order of your instruction, the registers that are used, or sorry, the register references. So remember how we said like 1 was referencing F. It might be like 0x20 next time, or 0x40. This for like each problem that you change. It's not going to be each run of the program. Each run of the program is going to be the same, unless you're talking about 17 and 18 of baby key. Those randomize each run, or should anyway. They randomize based on the some seed. But here, we know that this will always be arg1. So whatever we identified as arg1 will, that it'll be whatever this value is right here. So this is arg2, but the first byte from it. So that's going to be our arg1. And I'm just pointing out basically another way that you can identify what is your arg1, arg2, just because that's very important when you start writing your shellcode for things to operate smoothly and correctly. So this is going to be what's parsing what instruction happens. So we can right off the bat say if we call sys, this will be, whatever your arg1 is. So this might be like exit. So whatever the byte representation of exit is, which, if we wanted to do it by itself, well, just straight up looking at this function, where's exit at? Well, exit calls right here, which is 8.
8.
Yep. So we'll say instead sys 0x8. And what code do we want to exit with? And the only reason why I know this is because I've looked at it before, but we'll come back here. It then, so let's say display as. So it uses A to decide what the exit code is. So we actually don't use arg2 at all, which is fine. So we can just 0. But say we want to set an exit code. We'll say IMM, A, say I want to be exit code 69. I would do 0x45. Or 69, however you want your parser to do. And then it'll exit with code, or exit code 69. I wouldn't try to do negative numbers just because it wraps your bytes by 0 to FFF, and that's it. You can't do like negative at all. So that's all the syscalls, and that's pretty much all the instructions. Whew, okay, that's the... do you have any questions so far? Does anybody have any questions?
No, that was good. That makes a lot of sense.
Okay.
I mean, especially because you're showing how to derive it, but... oh my god, no wonder it fucking took Will 6 hours to derive.
Yeah, like...
yeah, this... I thought it was bad. I didn't realize it was this bad.
It's not, well, it's not that bad. Like, and I'm only saying that because once you have looked at this a few times, it kind of comes to you because you had looked at x86 and you can kind of correlate it. It's very similar in that regard. And once you start writing an assembler, the instructions are just like if you were doing x86. You can just say, all right, well, I want to then reference IMMA, and I want to load A or 0x23 into A, so I'll just type that instruction and it works.
Yeah, Colton, you missed it earlier, but I was saying like, oh, so the point of this is just to basically force us to like understand computer architectures the same regardless of. It's basically always the same.
I heard that part. I just
Okay, yeah.
I'm still a little confused as what the whole point of Yan86 is. So it's like a custom programming language that we're trying to reinterpret.
Right.
Into how it's interpreted in assembly. That's like just.
Right. Yep. Because this was originally reversing, right? So.
Yeah, it was. I would say it's not necessarily a custom language, but it's a custom what's called an instruction set architecture, which, yeah, basically a language, but it's different because languages are higher level in the sense. I guess it's a very minute distinction, but just because this is specifically like processing and it's instructions that we're iterating over in bytes that have to be compiled to, but.
Okay, I finally get now why if you do enough reversing challenges for long enough, it starts like you realize it's basically the same.
it's not, I mean, it's not always the same, but it's like you start picking up on little things. Like there's
The
stuff
pattern.
there's stuff that like Zion knows that he, like I said before, I look through stuff and I'll be looking at a challenge and be like, oh, well, it's this. And I'm like, why do you know that? And he's like, well, just because field knowledge. And I'm like, oh, that makes sense. You know, so I'll send a copy of this to just kind of.
Those are my own notes for these.
Okay. I mean, I'll just also send this too, just in case you're curious, or if anybody else is. Let's say also, so this is exit. We'll say if we wanted to do read mem. You know, look back here. I'm just going to do one of these just because these actually use 2 registers instead. So this will read mem, and it grabs a value from 21 and 22, compares them, whichever one is greater, or less than, I should say. We'll set that value to 9, or RDX 9, and then it will read that location in memory to some so sorry, it'll read whatever this register value is for the file pointer. So if say I want to let's say I want to read from standard in to a register. Wait. Read register, read write register. Sir, did I not? I thought I had a write mem in here. Am I just crazy? No, it was write register as well. Okay. Yeah. Sorry. Taking a second. Yeah, so read memory. And then what we would do here is we would say sys, and I'm going to say whatever the representation of read memory is, which is 0x10, and whatever the argument 2, which looking at argument 2 here, it gets not really used at all, it seems. So argument 1 is parsing it. Arg2 is used to define what register we're writing into. So that's nice. So we can figure out then, you know, we'll say 0x, I don't know, I don't remember, whatever switch case, and we'll say 0x1. So we're going to write into the flag register because we're cool like that. But I want to set where we're reading from. So I'm going to say like IMM. I'm going to put A, since that's what we use to actually do the file descriptor. I'm going to put 0 in there. And then to define what our buffer is, oh, shoot. You know what? I totally forgot about this. Okay. We're not writing into the register, necessarily. I'll explain, backpedal a little bit. So read happens. And read will take a file descriptor, which is figured out by 1020, right? So that's A.
Which is A, yep.
And then it will read to a buffer defined by B for bytes that are in C or B. So if I say like IMM B, and I'll say 0x23, and then IMM C 0x23 as well. They're the same, so it's not going to change any value or do anything weird like that. Now, the value that I'm putting here is actually not going to be what I'm writing to, because if we double back on this again, read will write to this memory buffer, which is not the register, which is fine. But if you remember, what does read return? Read returns a value. So if it was successful, if it was a failure, how many bytes it wrote is usually the success value. So it'll return to you how many bytes you were successfully able to write. And it'll then take that value as the second or the third argument to write register and write it into a register of your choice. Which is nice because then we can see our return value. So if I wrote into register 1, basically what we say is here set A for a standard in, and then we say set B for my fish brain already forgot buffer offset. Set C for num bytes. Oh, it just clicked in my head too what the reason why it does that weird switch. Why it does this whole thing of if it's greater than. It's because if the amount of bytes you're reading in is greater than the if your buffer size, so wherever this offset is greater than C, then you want to set it to be equal, just so you don't write further than that, just because it would end up wrapping around and go back to 1. So that wouldn't be good.
Yeah, that'd be bad.
Yeah, it would just keep writing in the same cyclical spot, which will overwrite what you wrote in the beginning. So that's what that's for. And then so it'll set to C bytes. And then we will say read. So this is the read mem, syscall. And then store return in F. And that's what that looks like. Just by the way, I did show you these 2 syscalls for a reason. They're very useful.
You also told us the bug for that for said reason.
Yeah.
For the vulnerability in said reason. So.
The world may never know. I didn't tell you how to do it though, so you have to figure that part out. But yeah, so that's this instruction set, and it's yeah, that's pretty much it. That's all you need to know for this. Now, let's say I'm gonna go into this next part. If any of you want to dip out, it's fine. I'm gonna start trying to write an assembler and show you how maybe you might want to write an assembler. So, we'll go ahead on that. So,
wait, I thought you showed how to do the assembler during the collaboration.
No, I made a disassembler. There is a difference.
Right.
there is a difference between an assembler and a disassembler. And I used a similar structure for both of them though, because the assembler part though, for the disassembler, we were given, so like for 14 here, when you're in main, you're given this VM code section, which is just a chunk of memory that's being interpreted. In 16 and up for baby key, and for 4 and up for the toddler, you're not given any memory. You're just saying, it's just you make some shellcode, have fun, and you have to make your own Yan code. So you basically have to make this. That's what you're doing. I mean, not the whole thing. It could be whatever size you want. I think it's like bounded by 765, but it's you have to make the bytes. And I don't know about you, I hate writing shit by hand. At least for this. I do not want to write 85, 08, 04 for each instruction and just try to like make each instruction by hand. That sounds like a pain in the ass. So, you write a assembler to do it for you. And like with all good projects, they start in Python.
Oh, I was about to say, I was like, oh, thank God. I was like,
yes, we're going to use Python for this. Just kidding. We're actually using Holy C. Strap up.
No, I thought you were going to like have to like write this from scratch or something. Like,
yeah.
You just took a good hour and a half just explaining us how all the instructions work.
Well, here's the thing. If you understand how the instructions work and you understand what I just explained, and that makes sense, this next part, I can pretty much just fly through, and it'll make some sense. So remember how I said before, actually, I'll also double back here, and we'll see, so there's also this concept of reference values for registers. So this is also going to be needed for actually making this assembler. When you look specifically to look for these values that I'm wanting, I look at the read register. And the reason why is because this has a huge switch case, and each of these cases is how we're going to refer to each register as with a byte. And these change each time. So not the 10, like this value, this 1020 value doesn't change, but what does change is this value. And that's important because that means that we can keep the references to C and A and all those. We can understand that those are 1020, those are 1022 and so forth, But that's not going to matter much because the program uses read reg and write reg, which use these switch cases to reference the registers. So we would say, you know, so if I start moving through these.
Wait, is that why they use a context-free? They were talking about like a context-free grammar for one of the challenges.
I don't think he was meaning context-free grammar. I think he meant CFG, which also stands for control flow graph.
Oh,
Yes.
I was like, oh, why they?
No, so
Okay.
I think what he was referring to, and I don't know who was referring to it, but that's this whole
Yeah,
thing.
that's why I was like, oh, that looks like a
Yeah.
CFG that they're talking about. Okay, that makes so much more sense now.
Yeah, that's normally how. So whenever you take a disassembly, you break it up by the branches, so like the if statements and stuff, and then the jumps, and that's how you can figure out, you know, where is the flow of my program going? How is the control flow going? And that's how you figure out basically your basic blocks, which are going to be the chunks of code that are divisible or divided up by that, and then yeah, that's pretty much it. And you can basically take from that then, where am I going in my program? I don't know if it was you I was talking to, I think it was, yeah, about the that pinball challenge in DEF CON. Also, I can hear myself, by the way. I think it's on your computer too.
Hold on, let's figure this out. What happened?
All right, so you remember that pinball challenge?
Yes, from DEF CON.
So that's what the basic blocks are referring to, and then that's how those are created, and that's the control flow graph. That's what that is. So this is just quick of what that is, and the reason why they were talking about that is because when you analyze this, you can go about this two ways. When you analyze like the program he gives you, the VM code, you can take the code, and you can make a disassembler and then a decompiler, or not decompiler, but a emulator for it in Python, which is another way of doing it, because then you can see what the memory values look like and how it's, you know, dynamically running the program. The other way is to take the disassembly and basically walk through it, which is I think what FreakMod did. He walked through how the program is executing its code and how the register states might look like, just doing it statically. And that's a totally valid way of doing it, but it really helps if you break it up into basic blocks, because then you understand, you know, what chunks are going to be executed at a specific time if I jump to this segment in the code. So, but for this, we're not going to be doing that. So anyway, so again, so this is case 40. Some of these might be like case 20, and then I don't know why this is here. This is nonsense. It doesn't need to be there. But like case 4. It's referencing 1021, which is B. So I'm going to go through real quick. And we are going to define, so say A, B, C, D, S, I, F.
And you can go through the case statements for each of those values.
Yep. So I'll say 0x40, and we'll say, so that's for, I think that was for 1020. Yep. So 1020. And then 402, so 1026 is case 1. So this is 0x1, case, so 2, 1022, so that's C, so 0x2, and then case 4 is 1021, so 0x4, case 8, so 0x8 should be whatever 1023 is, 0, 1, 2, 3, 0x8. 401, which is 1025, 0x10, I believe 0, 1, 2, 3, 4, oh no, this is 0x10. And then case 0x20, I know this should be I, this is 0x24, or sorry, this should be S, 0x24, or not 0x24, but 0x20, there you go. So, just looking at the last value real quick. So I would right click on this, basically display as decimal, and then we just check what case it is. And that's how I assigned those. So cool. Now we know what those are. And so the stuff that changes for these, like I was saying, this is one of those values that change. The instructions will also, the switch cases, and then the syscall values will. And I'm not going to write all of those down. I just figured the registers might be a little bit more important to point out, because that's how you, this is how you reference all the registers. But this is just one of them that changed. So instructions and syscalls and registers are going to be what changes the most. Technically, the flags for jump also do, but that might not be important to you. It may be, but if you're writing shellcode, it probably isn't unless you're using those specifically. So just keep that in mind. So like whatever represents like a greater than will be different in between two challenges.
Fantastic.
So I'm going to set up my reg. So I'm going to make a dictionary, kind of like I was doing in the implementation that was in the office hour, or not the office hours, but the collaboration one. So I'm going to make a reg dictionary. We're going to have ints dictionary, which is going to have my instructions. And then I'm going to have another one that's going to be my syscalls. Scall, or sys, let's say syscall. All right. And, well, yeah, cool. Let's do that. So then for the registers, we should have and actually, you can make these in bytes or string. I'm going to do bytes. So do I'll wait for that for now. B, colon, comma, C, and then D. Just keep doing these other ones. And then once you get this done, the only things, like I said, you'll need to change are those registers that were mentioned and the instructions in syscall, and the rest of the content's pretty much the same. So this would be 0x40, and then B is 0x4, C 0x2, 0x8, 0x20, 0x10, and 0x1. Now, instructions have a similar problem, right? So we'll have to go through, and I'm going to lay these out in order for the function calls. Because when we look at interpret instruction, I'm just going to put these in order just to make it easier to reference whenever I go back through this for the next challenge. So when this instruction, or this statement right here, correctly evaluates with an ampersand 4, so bitwise and a 4, it'll come out to IMM. So I'm just going to do this in order. We'll say ooh, that's not right. IMM, or we could do lowercase, however you prefer. I'm going to do uppercase. I really just wanted that indented, didn't it? Add STK. By the way, you don't need to do this. But
Well, I mean, it makes it easier than writing the.
oh yeah,
Right.
it most definitely does. I think the next one's what, compare? Yeah. Let's compare. And then JMP. And then I think that's it. Oh, and sys. Can't forget that one. That's the most important one. And then, like I said before, I'm just going to go through then and look at each of these if statements. If it's and ampersand 4 or ampersand 10 and so on. Now, the only one that's really weird is this one right here. If you notice for STK, it says if this value is less than 0. Now, there is a reason for this, and this has to do with a weird decompiling thing, why it shows it like this. But what it's doing is it's trying to represent 0x8. If we look at, oh god, hold on 1 second. Here. Cool. So, if we look at, so I'm gonna disass, what was I looking at? Interpret instruction, and we look at that specific instruction, which should be, see, JNS right here, this guy, because interpret stacks right here. So JNS, when it tests, this is to make sure if the byte is signed. So it jumps if it's not signed, which means it doesn't run this function if it's not signed. Now you might be wondering, because this is an integer, which an integer is a 4-byte value, or in this case might be a smaller than that value. Let's look at IPython real quick. And also, the way this also might be shown, let's look at Binary Ninja again. It checks as arg2, or sorry, this guy, arg2, wait, come back here, arg2, there we go, I'm blind. And just make sure that it's less than 0x0, or, yeah, 0. And the reason is if it's signed, basically, if you remember the idea of signedness, means that your bits are, you have like some one value up here, and then this would be like all zeros, and then a couple other bits scattered throughout. But because this upper bit was set, it means this is a whole signed value, right?
Mm-hmm.
But if you have 0,
You have the one
yeah,
means positive.
right.
But
If you have
one means negative, 0 positive, yeah.
Yeah, exactly. Then now, if you think of this too, if I have 0 be 1, like that, you know, it's 32. This one's 64. 0x80, I think. 128. So if we do bin of 0x80, that's what that looks like. But if you say look at like 40, this is smaller. And if you make it to the same bit size, it actually looks like this. So it's not signed at all because this upper bit's still 0.
Mm-hmm.
But the only one that is actually still 0, or is 1, is 128, which is 0x80. So just, that's my reasoning for that, and I'm sticking to it. Took me a second to figure that out too, because I didn't, Ghidra does that too. I was like, why is this fucking doing this? I have no clue. So I'm going to pop through these real quick, and we will, I'm going to do this.
Finish up the dictionary.
Yeah, I'm going to finish up this dictionary. If I can type in my, so 0x4, 0x10, 0x80, 0x2, 0x8, 0x40, 0x1. Apologize, it's taken so long. And then I think this is, yeah, 0x20. So that's cool. Now syscall. So we're gonna look, bring this back, and we're gonna look through our syscall again. What am I at for time? An hour 43. Damn, that's not too bad, I guess. So
Yeah, but that's what I was saying. Like, you spent an hour and a half to explain all the instructions for us.
yeah. Now the syscall, we're just gonna do the same thing. So we're just looking at the if statements, and if it, and you'll notice that all these numbers are very similar. So they're all either, and you'll learn this if you do 17 or N18. All of these, the registers and the instructions and the syscalls are all based on a pool that's either 1, 2, 4, 8, OX10, OX20, OX40, or OX80. So it's only those. And that's the reason why is because they are evenly, that you can ampersand them or bitwise and them with something, and it'll either be 0 or the true value if it's a valid representation that's trying to interpret. So if you ever have a value that's not any of those, you are either grabbing the wrong argument, or it's not a valid instruction that you're pulling in. So reevaluate what you're doing, and that would be what's going on with that. So just keep that in mind if you're ever doing these. So I'm going to go back there and do the same thing here. So we're looking at, let's see, what do we have here? We have open. So we have open. I'm just going to, this is read code, read mem. And then after read mem is write. And after write is sleep. And then exit should be after this, I believe. I'm looking at all of these. Exit is 8. So OX8. OX8, OX2. OX20, OX10, OX4, and OX1. Okay, cool. So this is pretty much the core of what you're going to need to do. And then the next part, for the assembler part, is just a simple parser. And the parser is going to parse basically your instructions and turn it into bytes. So whatever instruction, like if I did IMM A3, how does that translate into bytes? And another thing we're going to need to that also changes each time is the order of your instruction. Remember, so whether it's if the opcode is byte 012, arg1 is 012, arg2 is 012. This is important. So we'll do op order. And we already said, what was it? Arg0 is, I think, 2. And then arg1 is 1, and arg2 is 0. That makes sense, right?
Mm-hmm.
Okay.
So now to parse it together.
Yes. Now parser, user in. So parser. All right. Actually, probably shouldn't have that there. So parses. So now what we'll do is, or at least what I like to do is, I'll say parsed equals user in, and I'm gonna assume that the bytes, or what I'm gonna be passing in, is bytes, just because I like everything in bytes. It's easier to write to a file instead of having to do other crap to it. So I'll just do .split, and then we'll split it by space. Because if we remember how this looks, for an example instruction,
Right. Yeah.
3. Yep, so it'll delimit it by this. Then we'll say, basically for each one of these, we're going to change them into their byte representation. So the op is going to be insts, and we're going to pass in
0.
parsed 0.
Oh. There it goes. Yep.
Okay, and then
Because it's always gonna be the first one.
exactly. Now, there's a possibility for arg1 and 2 that those values might be 0, or may not be a valid register. And the reason for that, because so you can have, for example, so you can have STK 0A or STK A0. You can also have IMM A 0x45, which is 45 is not a valid instruction or a valid register. So because of these values, you kind of have to do a little funk with what you're doing. I always like to do try catch me, or not try catch me, try hack me. Jesus, try catch. So we do try, and then I'm gonna replace that except, and we're gonna do that for both of these. So try pass, accept pass. So this one is for arg1. This one is for arg2. So cool. Now what we'll first try to do is try to interpret it as it would be a register. So we would hope that this is a register. So we'll say reg, So reg, or whoops. We'll say arg1 equals reg parsed 1. And then if it's not, we will instead say arg1 equals the byte representation, or the, I guess the hex representation. So you can do this a couple ways. You can either have your instruction, or the value there, be a 0 or a 2 or a 0x2. And that's up to you. I like 0x2, it's just easier to read the code that way. Have it a hex representation. So you would say something like parsed 1, and then you would say the base, so it would be 16 because it's base 16. And that would be what you do. You basically do the same thing for arg2. So actually, I'm going to just copy this. And then we'll do this, and we'll change which one we're using here. Cool. So it's arg1 and arg2. And then now you have to create the instruction. So a way that I thought that was pretty neat to do this, so we had instir equals byte array. So bytes 0x00, 0x00, 0x00. All this is doing is I'm creating an array that's specifically called a byte array, so I can directly address each index in this instruction and modify it to whatever byte I want. So I can say this equals now /x41, which would be an A.
Mm-hmm.
And this is also now where the op order comes in big handy. So we'll do instir. I will say op order of 0 equals op. Instir op order 1 equals arg1. Instir op order 2. Ooh. Order 2 arg2. Does what I'm doing here make sense?
Yes. Wait, hold on. Because I understand arg1, arg2, then...
Here, I'll explain this last part. This last part's a little weird. So remember that array, that op, so op ord?
Yes.
So I said,
It's 2, 0,
2,
1. 2, 1,
0. Yes.
Yeah.
Now what this is it's actually your opcode, your arg1, and then your arg2. Because remember, our opcode is in the byte 2 position, our arg1 is in the byte 1 position, and our arg2 is in the byte 0 position. And we saw that when we were reversing it. That part makes sense, right?
Yes.
Okay. Now what this is doing is each time if I reference order or op order at index 0, I'm going to be looking at what position is the opcode in. So it'll return back a 2, and then it will set the instruction at byte 2 equal to the opcode. Does that make sense?
Yeah. Kind of.
So, because if I just said instir 0 equals opcode, that would be wrong, right? Because the opcode should be in the second byte position of the instruction.
Oh, yeah, that's right. Okay, because it's all funky and weird like that. So that's how we're mitigating that.
So this is basically how I'm keeping this in a dynamic sense. How if I change just one of these, if I could change this to 1, this to 2, well, now the opcode's in the byte 1 position, and the arg1 is in the byte 2 position now.
Mm-hmm.
So this makes it really easy if, like, say I'm changing my program to match whatever the new challenge is. I just say, all right, well, this is 1, this is 0, and then this is 2. And now my instructions have completely changed when it compiles. And perfect. Now it'll, just be in the correct order based on what I put in this, in this array.
And that you only knew that because you looked ahead and noticed that it does change.
Well, yeah, because when I went through the challenges, I noticed that each time I did a challenge, everything, like what I specified here, all these elements that I'm dynamically making are going to change. So this is why I have them at the top of the program, so that I don't have to go dig for them. This changes, registers change, inst, and syscall. Those all change. So you hunt those down, and you can basically make your shellcode pretty easily then. Because, like I said, this parser, all the same. How it actually goes through all this stuff, all the same. But it's just a matter of just need to change those values, and you'll be able to basically have what you need.
Surprised Colton didn't say kill me.
I hope he's there. I wonder if he fell asleep. Cool. So we sign the instruction, and then we just throw it back, and then we return and stir. So now we get this byte string back, and now we can do something with it. Another option you can do is return a bytes, because something cool about byte strings is you can typecast it. So if I did like x equals byte array of bytes 0x01, 0x02, 0x03, well, it'll look like that, but then I can actually just say bytes and then typecast it to bytes instead, which makes it really nice. So you don't have to like do any funky shit with it. So what I'm doing here then is I'm just saying, all right, well, we'll just turn it into a bytes type and then return it. Okay, on the last leg here. Ready?
Reading your input.
Yep, now it's just making your shellcode. All of this is done. We just need to make the shellcode happen. So I'm going to do a simple exit function. So I'm going to say sc and like this. And actually, we can either do it with multi-line stuff, or we can just do a single line. I'm going to do single line for now. I'm going to make it a bytes type, or you can make it string and then just do dot encode afterwards. It's up to you. But I'm going to do imm a. I want that to exit with 0x45, which is 69. Then we'll do sc plus equals bytes. So we have our exit code, which is an a, and then now we're going to call sysexit. So we'll sys and then exit, and then I want the register to be D. I want the return code to go into D, or whatever, result. It always puts a result into something. Actually, exit doesn't do that. I take that back. Remember what we looked at before? So
yeah, it's 0. It's whatever A is.
Yeah, this value does nothing. It's just whatever. So I put 0 there. Now let's go ahead and we'll say because this is separated by a new line, we can make another function, which I have is called ASM, which we're all familiar with what that does. We can then do final. I'll set that as empty, and then for value, or actually probably parsed might be a better word. And we'll sc dot split. And we'll do another like that, and then for inst in parsed, I'll have that final value. Final equals b. Do final plus equals parser of inst. And then we return final. And then I'm going to go ahead, since I don't want to write it to a file at the moment, you can choose what you want to do with this, but I'm just going to go ahead and print out then, so I'm going to ASM, I'm going to pass it my shellcode, and I'm going to do .hex because it'll return a bytes object, or a bytes object. So I'm going to just print out the hex of it, just to make sure it compiled correctly. Okay?
Mm-hmm. And
Moment of truth. Let's see if this works.
first try.
Was this assembler? F. All right. So figure out. So key
47.
error. Oh, this was okay. This was something else I ran into. So okay.
Wait, the arg1.
Yes. So the reason why is because I put exit. Now exit is not a valid register, nor is it an integer. So what we can do is we can also be a little bit jankier here, and we can say here. So if it doesn't, if it fails this, which would mean that it's not a register and it's also not an integer, then it's probably a syscall. So we'll say then arg1 equals syscall, and then we will send that parsed 1. And this should be the only case when that happens. Exit or the syscall name is usually not in the second argument ever. So when we ooh. Cool, there we go. And that's your assembly.
Instead of having to like look up every single one and manually hand jamming it.
Yep. So you can just now go through, and I can write this out. So if I wanted to say, let's do, what was the syscall one? So I'll just say, let's go to sys here. Say if I wanted to read from standard in, so I'm gonna do read mem, which is here. So read memory. So I'm gonna read memory and make sure I pass into a 0, and then I'm just gonna do FFFF for both of those. So it's gonna read into, like we were talking about before, the maximum amount or whatever. So I'll IM a, and then I want to read in from standard in, and then IM b 0xff, and then sc plus equals b, and we'll do IM c 0xff, and then sc plus equals, actually I'm going to do 4.5 here, or yeah, ff, that's fine. And then b, and we'll do syscall, actually sys I think is what I did, right? Yeah, sys, okay. We'll do sys, and then we'll do read mem, and store the result in D. Let me just double check that my nomenclature is right. Yeah, read mem. And that's going to read mem. And now if we wanted to exit cleanly, we'll do sc plus equals. And, you know, we can add our exit stuff. So I'm going to put the exit code of 0. Well, 0 is already in there, so I don't really got to worry about that at the moment. But then I can just do sys exit 0.
And then it does everything for you. Or your script does everything for you.
Yep. There you go.
Oh. Did you really expected us to do all this? Or at least elite people, I guess.
I mean,